Alright, so the purpose of this video is to describe to you mathematical modeling. Mathematical modeling. Alright, now I'm going to just essentially write some notes, and hopefully by the end of this you'll be able to understand mathematical modeling a little bit better. So basically a mathematical model is it's an equation or a bunch of equations that describe the essential features of some natural system or some process, and it does so in mathematical terms. So there's always like an equal sign. So for example, Newton's second law, F equals ma. This is a mathematical model. It's a very well tested model. Actually, it's originally written as acceleration is equal to the net force divided by the mass. And it's a mathematical model that says, okay, the acceleration of any given body is equal to the net force directly proportional to the force, inversely proportional to that object's mass. And this mathematical model is useful because it allows us to make predictions. So mathematical models have a few characteristics. I'm going to just write them down. So first, it describes a natural system or process. Natural system or process. Second, and an important part of it is it represents just a simplification of reality. So it represents a simplification or an idealistic representation of reality. Now, what does that really mean? For example, can we say that the acceleration of some object is truly the force, the net force, divided by its mass? Well, actually, that's not 100% true, because we know there are relativistic effects. If you have a very, very large mass, like the mass of the Earth, or even larger than that, actually, the mass of the Sun, then what happens is this equation doesn't become accurate anymore. Its predictions might give approximations, but they no longer are very accurate. So you need a different mathematical model to describe that, and that's what Einstein's theories are. They're another mathematical model that describes better the acceleration of and the motion of very large systems and systems that are traveling very, very quickly on the order of the speed of light. So that's what it means by it's a simplification of reality. Really, we neglect things that were features of the system that aren't very important to the behavior that we are interested in. Lastly is they give reproducible results. So reproducible results, and allow us to make predictions. So that's the gist of mathematical models, and in one of the next videos we're going to talk a little bit more about some examples. We'll do a falling parachutist example with Newton's second law, But before I move on, there are conservation laws that we use in science and engineering to help us develop mathematical models. So, conservation laws, and these are very important mathematical models or laws in science, and there's many of them in that have to do with all different types of systems, but the general idea is behind all these laws is that change in any system with respect to some parameter, maybe time or space, is just equal to the increases in that system, increases minus the decreases. Let me give you a simple example. One simple example is if you have just a four-way pipe junction with flow. So maybe you have something that looks like this. And let's say coming in here, we have a flow in of 100 units, whatever liquid or fluid we're talking about. And here we have a flow inward of 80 units. And let's say down here we have an outward flow of 120 units. Then what would be the flow in or out of this pipe? Well, we know based on just conservation of this fluid that if we've got 180 flowing in, we need to have 180 flowing out, right? If there's going to be no change. So, well, let's give an example where there is change. So if we have, let's say we've got 20 going out here. If we have 20 going out there, so what is going to be the net change in the over amount of fluid in here? Well, we're going to have the change, remember, is equal to the increases minus the decreases. So the change increases is what's going in, so we've got 180 going in minus how much is going out, 140. So the net change would be a positive change of 40. So we're going to have 40 more units in this pipe flow. Now, change, we are specifically in engineering and sciences, we like to measure the time rate of change of things. Time rate of change is important to us. So, time rate of change. That changed. Sometimes I can't spell. And this has a special name. We call it transitory behavior, transitory or transient. And it usually involves the time derivatives of some property. So maybe velocity, the time rate of change of the velocity, and we'll do an example, or the time rate of change of the concentration of some species, or the time rate of change of temperature. These are all things that we're interested in, and these rates of change can typically be modeled using a conservation law. Now, the other thing that we're interested in typically in science and engineering is, so this is called transitory or transient behavior, transient problems. What happens if our change what happens when change is equal to 0? Well, if that's the case, then we just have the decreases are equal to the increases. And we call this type of problem the steady state problem. Steady state. And so if we just use our pipe problem as an example, draw this again. So if we've got 80 coming in here, we've got 100 coming in here, and we've got 120 leaving here. If I say this is a steady state problem, meaning there's going to be no change, net change in here, then I might ask you, well, if there's no net change in here, then what is the outflow here? Well, because we know increases equal our decreases, then we can say, 180 is what we've got going in. It's supposed to equal to what's going out. So 120 is going out plus x. Then we can solve for x. And should come out to be, let's see, 180 minus 120 should x equal 60, right? There we go. So we can figure out here that this is 60 using a conservation law. Alright, let me think here. Is there any other parts that I want to describe about this? Well, mathematical modeling is really important. That's what we do in physics and engineering. We develop mathematical models, and this class really isn't devoted to studying mathematical models. It's how to solve mathematical models. So in this class, we're not really going to develop, will not develop models. That's what we do in other engineering classes. Develop mathematical models. But we're going to learn how to solve them numerically using computers. So we're going to learn how to use a tool to solve them. Now, if you can solve them really well, why do we have to learn about them? Well, it's kind of important to learn about them because, it's kind of like if you were, if you had some really awesome tools to fix a car, but you didn't know how the car works. If you don't know how the car works, doesn't matter how good your tools are, you're not going to be able to fix it. Well, computers are great tools, but if we don't understand numerical methods and how to apply them to mathematical models, then we can't use them very effectively to do our job. So anyways, that's going to be it for this video, and we'll see you in the next one.